Now, relation. Relation. In relation, let A and B be two non-empty sets. Then, a relation R from A to B is a subset of A cross B. So in relation also, we write the elements in coordinates form, like first of all A and then B. So they are a subset of A cross B. Thus R is a relation from A to B. So this implies R is a subset of A cross B. So R is a subset of A cross B. If A comma B, now also if A comma B like this belongs to R. Now if A comma B belongs to R, then we say that A is related to B, and we write A R B. So A is related to B. Now if A comma B does not belongs to R, then we write A is not related to B. We write A is not related to B. Now domain, range and codomain of a relation. Let R be a relation from A to B. Then let R be a relation from A to B, then R is a subset of A cross B. Okay. Now the first point is that what is a domain? So domain is a set of first coordinates of element of R called the domain of R, written as domain of R. So domain of R will be the first coordinates of element. First coordinates of elements of R. So that will be the domain. Now the set of all second coordinates of elements of R is called the range of R and is denoted as range of R. So that will be the second coordinates of elements of R. That will be R. And set B. Now what is the codomain? Codomain is the set B. So codomain of R is set B. Codomain of R will be the set B. Now there is also an arrow diagram. Now in arrow diagram, let R be a relation from A to B. Now then we draw a two bounded figures to denote A and B. We put the dots to represent the elements of A and B, and for each, like A comma B belongs to R, we draw an arrow from A to B. So this will be this, like, I will be okay. So let's take an example to understand it better. Now A is what? A is, suppose A is 1, 2, 3. Take B as 2, 4, 6. Okay. Now the relation is given to you. Now R is given as like 1, 2, 1, 4, 3, 2, 3, 4. Now this is what the R is given to you. Okay. Now you have to show that R is a relation from A to B. Now see, if we do A cross B, so A cross B is going to be 1, 2, 1, 4, 1, 6, 2, 2, 2, 4, 2, 6, 3, 2, 3, 4, 3, 6. Now from this we can clearly see 1 comma 2, 1 comma 2, 1 comma 4, 1 comma 4, 3 comma 2, 3 comma 2, 3 comma 4, 3 comma 4. So basically if we take this as a set A cross B, then this set contains all the element of set R. So R is what? R is the subset of A cross B. Hence by the definition R is a relation from A to B. So R will be a relation from A to B. Now, so R is a subset of A cross B, hence R is a relation from A cross B. Now, what is the domain of R? Domain of R. We know that domain of R are the first coordinates of elements of R. So 1 and 3. So domain of R is 1, 3. Now, range of R, let's find the range. Range of R, we know that range of R is the second coordinates of elements of R. So this is 2 and 4. 2, 4. Codomain. Codomain of R, as we know, codomain of R is the set B. The set B is what? Set B is 2, 4, 6. So codomain of R is 2, 4, 6. And now suppose we want to show this by the arrow diagram as we have discussed. So for the arrow diagram, as you know, we draw two bounded figures to denote A and B. So let A, this is A, this is B. Okay. Now A is 1, 2, 3, 1, 2, 3, B is 2, 4, 6. Now again looking at the relation 1, 2, 1, 2, 1, 4, 1, 4, 3, 2, 3, 4, 3, 2, 3, 4. So this is how you represent this by the arrow diagram as shown alongside. Now, we know that 1 is related to 2. So 1 is related to 2. Similarly, 3 is related to 2. 3 is related to 4. Now 1 is not related to 6. Just a way of writing 1 is not related to 6. Now binary relation on a set. Let A be a non-empty set. So we take A be a non-empty set. A be a non-empty set. Then every subset of A cross A. Now taking A as a set, and then every subset of A cross A is called the relation on A. Now since phi is a subset of A cross A. So basically phi is a relation on A called the empty or void relation on A. Similarly, A cross A is the subset of A cross A. So A cross A is a relation on A called the universal relation on A. Similarly, if IA, now this is defined as like A comma A, such that A belongs to the set A. Clearly IA is basically IA is a subset of A cross A. IA is a subset of A cross A, and therefore it's a relation. It's called the identity relation on A. Now we take an example. Now A is given as 1, 2 and 3, and R, which is a relation. Now R is 1, 2, 2, 2, 3, 1, 3, 2. So this is a relation. Now R is what? R is a binary relation on A, because R is what? See, if we find A cross A, now if we do A cross A, which is 1, 2, 3 cross 1, 2, 3. So this will be 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So as you can see, R is a subset of A cross A. So R is a relation. So R is a subset of A cross A. Hence R is a relation on A, which is also known as the binary relation on A. Now suppose if we have to find the domain and the range. So domain of R, we all know, is the first coordinates of elements of R. So that is 1, 2, 3. 1, 2, 3. Sorry. Range of R will be the second coordinates 2 and 1. Means 1, 2. So that is the range. 2 will now again we take an example for the illustration. Okay. Now here we take n. Be the set of all natural numbers and let. Now see, R is a relation now which is given as A, B, such that A, B belongs to natural number and the equation is satisfied. It's 2A plus B equals 10. 2A plus B equals 10. Okay, now we have to show that R is a binary relation on natural number. Find its domain, range and codomain. Okay, now suppose first of all we will write the elements of R. Now if we solve, R is basically, see they are saying 2A plus B equals 10. Now if you take A as 1, B as 8, that is 10. 1, 8. Second is 2, 6. 2 into 2, 4 plus 6, 10. 2, 6. 3, 4. 3 to the 6 plus 4, 10. 3, 4. And this is 4, 2. 4 to the 8 plus 2, 10. So 4, 2. Now see, this is what the relation is. Now obvious that this is actually the subset of n cross n. Now we know that now this is not n, will not be possible to go for n cross n, because n is a set of all natural numbers, this is a set of all natural numbers which will go to infinite. Basically R is the subset of n cross n. So R is what? R is a binary relation in n. R is binary relation in what? In n. Now again, domain of R. Now we can find it here only. So domain of R is the first element 1, 2, 3, 4. 1, 2, 3, 4. Range of R, that will be 2, 4, 6, 8. 2, 4, 6, 8. So this is the range of R. And again, to find the codomain. Now codomain is basically the set B. So this is what? A, this is B. Codomain is n, natural number. Okay, now the types of relation. Now the first part is the reflexive. Reflexive relation is like if A comma A belongs to the relation R for all A belongs to capital A. A is an element, this is a set. Then we write as like R is A is related to A for all A belongs to A. So that is known as reflexive. Like an element is related to itself in a reflexive relation. Second comes the symmetric. If A comma B belongs to R, if A comma B belongs to R, this implies B comma A belongs to R. So B comma A belongs to R. So in short, what I mean to say is that if A is related to B, this implies B is related to A for all A comma B belongs to A. A comma B belongs to any relation A. And third one is the transitive relation. Transitive transitive relation. Now in this case A comma B, if A comma B belongs to R, B comma C belongs to R. So this implies that A comma C belongs to R for all ABC belongs to A. For all ABC belongs to set A. This is a transitive relation, or in short we can write if A is related to B and B is related to C, so this implies A is related to C. Okay, then comes an equivalence relation. Now, equivalence relation is that relation which is reflexive, symmetric, transitive. So that relation is known as the equivalence relation. Now, to illustrate this, we can take an example. The example is, suppose m is a positive integer and R is a relation A comma B. A comma B belongs to integer and A minus B is divisible by m. Now what we will do is that we will show that R is an equivalent relation on C. So starting with the first one, so we start with this A comma B belongs to integer, A minus B is divisible by m. Now starting with one, let A belongs to integer. Then the first part is we do A minus A, which is 0. Now A minus A is 0, which is divisible by m. Now 0 is divisible by m. So A comma A belongs to the relation for all A belongs to Z. Hence, this is what? This is reflexive. So this relation is reflexive. Second, to prove it, second was symmetric. Now if A comma B belongs to the relation, so that means A minus B is divisible by m. That is, if A comma B belongs to a relation, then it's obvious A minus B is divisible by M. So if we put a negative sign, minus of A minus B, this will again be divisible by M. Or we can write this as B minus A, which is again divisible by M, which will be obvious that it will be divisible by M. So this implies B comma A belongs to the relation. Hence A comma B belongs to this relation. That means A is related to B implies B is related to A. B minus A. Like A minus B is divisible by M, B minus A is divisible by M. Proof. So this is symmetric. Symmetric relation. Now third point. Now A comma B belongs to R and B comma C belongs to R. That means A minus B is divisible by M. B minus C will also be divisible by M. B minus C will also be divisible by M. Now adding these two. Now sum of these two, A minus B plus B minus C, that obvious is will be divisible by M. Adding these two, A minus C is divisible by M. So A comma C belongs to R. So A related to B, A related to B, B related to C, A related to C. So this is transitive. So as we can see, R is what? R is reflexive, symmetric, transitive. Hence this is known as, so R is an equivalence relation.